Hello everyone, it's me again. This is also going to be a bit tired because I'm recording this at 2 a.m. But yeah, this is the video for Statistics Problem Set 3. It's quite a difficult topic, personally. For me, it's comparatively from the other stuff, it's a bit more difficult. But we're going to go through it today and hopefully I can help you guys out. Of course, my usual disclaimer. But just because I've written it down doesn't mean it's right, okay? Remember, go check with your tutors, go check with Dr. Tinkani. Professor Tinka. Whatever she is. Go check with her. She knows more than me if you're having problems, okay? But right now, this is just a quick and easy way for you guys to get information. Anyway, let's get started. So let's read the first question. It's important that airlines follow the published schedule departure of times of flights. Suppose that one airline recently sampled the records of 246 flights originating from London and found that 20 flights were delayed for severe weather. Okay, so we have out of the 246, 20, that's not realistic at all, 20, something like that, get delayed for severe weather, and 4 were delayed for maintenance concerns. So 4 for maintenance. Compute a 95% confidence interval for the percentage of...
I'm having trouble connecting to the internet.
Yes.
Take a look at the help section in your Alexa app.
I'm well aware you are. Just because I say... Sorry. Whenever I say the word computer, my Amazon Echo kind of just sets off. It's not even connected to Wi-Fi, anyways. So maintenance is going to be 4. So what it wants here is percentage, right? So we're going to be using the proportion thing. Now, I've got my my sort of slide here. This is my my solutions, but I've also got this formula sheet here. I hope you guys can see this. I have sent this to the chat, to both chats. I'll send it again if anyone else requests it. But essentially, having a good formula sheet is useful for this. So I'm going to grab the formula for population proportion, which looks a lot like this. So we have the real proportion of on-flight timing, which is equal to the sample proportion plus or minus z alpha over 2, square root of sample proportion 1 minus sample proportion over n. This is our formula, essentially, for the interval, okay? So add and subtract, that's going to be our interval. So let's first of all define our terms. So what it's asking here is the percentage of on-time departures, which is going to be the 246 minus our malfunctions. So as you can sort of see there, 246 minus the 24 malfunctions, that is going to be 222 flights out of 246. So that is going to be our P line one. We've also know that n is equal to, well, fairly obviously 246 here, because that's our sample size. And z alpha over 2. Now this one's a bit trickier. Okay, so let's look at a normal distribution just to figure this out. Okay, so think of a 95% confidence interval as taking up 95% of the graph, right? So we're going to cut it off at this side and cut it off at this side. Okay, so 95% is covered by these areas. So what is each area going to be covered by? Well, then this is going to be 2.5%, and this is going to be 2.5% as well. So if I wanted to figure out the area of this or the area of this, how would I do that? I could either use a cumulative distribution, and I could calculate area above minus area below here for the right one, or I could just calculate area below on the 2.5. So I'm going to quickly do that. Where's my calculator? Look, when it's this late, it's not like great for me. Where is it? Where'd it go? One moment. I found it. Okay. All right. So what we're going to do is we're going to use the inverse calculator function. If you're using one of these, A lot of A-level students normally have these because they're normally required. But just so you guys know, it is a Casio FX991EX calculator. If you use I don't know if you guys can kind of see that. It's called an inverse normal function. It's there on number 3. If you use that, and then you type in the area you're calculating for, here I'm going to calculate for the 0.025 area. So I'm going to type that in, 0.025. Because we've normalized it, essentially, we're leaving the sigma as 1 and mean as 0, and you should get that value. Now, of course, you've got to use the main value, but essentially the point is that the value you should get is that z alpha over 2 is going to be equal to roughly 1.96. Roughly that. Okay. If you want to be a bit more specific, add more decimal points, go ahead. But that's essentially what happens. Okay. So rewriting our equation, we get P is equal to 224 over 246 plus or minus the 1.96 square root of, so 222, 246, 1 minus 222, 246 over 246. Okay, and according to my answers, you should get, that's the wrong thing, you should have a interval between roughly 0.86537, again I did this in detail, and 0.93951. Again, you can round. Putting it to 0.87 and 0.94 will probably still work. I'm just doing it just so I'm completely covering all my bases. Now, for the other one, it's asking for a 95% confidence interval for the occurrence of severe weather. Now, we know severe weather occurred it occurred 20 out of 246 times. So we're going to rewrite this, 20 out of 246, plus or minus, and remember, we're going to use that same value of z alpha over 2 because it's the same confidence interval. So 1.96 again, and then we're going to do the same thing, essentially. So 20, 246, minus, no, it's times 1 minus 20 over 246 over 246, and you should get a interval, as far as I'm seeing here, of roughly 0.047, yeah, 0.047 and 0.115, roughly like that. Okay, as you can see here on my screen, it's a bit more accurate, but then again, that's because I'm a bit extra. Okay. A psychologist wants to estimate the sample variance of employee test scores. So we're estimating variance here. That's our first little thing. A random sample of 18 scores, so let's write this as we go along. N is equal to 18. Had a sample standard deviation, which we're going to call S, of 10.4. Okay? It wants us to find a 90% confidence interval. So first of all, let's start with the confidence interval. What is that going to be? Okay, once again, if we look at the normal distribution, and we think of like, okay, this area is occupied 90%, then each of these areas are going to be 5%. Yeah? So we're going to do the same thing. We're going to put 0.05 into our calculator and then calculate it out. That is going to give me roughly 1.644853667. Yeah, I don't know how you guys want to phrase that, but that's what I've got. Just put it into your calculations. You can shorten it however you like, but that's what I am going to put it as. Come on now. Also, if messes up, it's because Windows has tried a new version of Whiteboard, and I am not a fan. It's just a bit annoying. So what we eventually get here is that we're going to use this formula. If you guys can sort of see that, again, if you can't see it, look up. Wait, I remember this now. Okay, scratch that. Okay, for this one, we're not actually going to use the normal distribution. We're going to use the chi-squared distribution. Now, chi-square is obviously a bit tricky for people who haven't done it before, but it is a staple of statistics. Basically, chi is just a funny way of writing x. Okay, so chi-square, and we're going to do alpha over 2. All right. We also, okay. Right, we're going to use a chi-square calculator. I believe I have it in the formula sheet. Yeah, there it is. Okay, so we've got the chi-square calculator. Hopefully that opens. Here it is. Okay, so what are we operating on? So we want to go to the inverse, remember? We've got a 90% confidence interval, so that 0.05 is going to stay the same. And we have got, well, how many people are there? Let's check again. 18 people. So we're going to do -1 of that. So you always want n minus 1 degrees of freedom. So 18 becomes 17. So we get that. And you should have 27.58. Let me just cross-reference. Yep, that should be it. Then you want to go on the other side. And you should find the, so again, try thinking of it like that. You've got, even though we're not necessarily following an order distribution, imagine you're calculating for 5% first, and then you're going to calculate for the remaining 95%. And then you should be getting 8.6. Yeah, that's it. Okay, so once you've got those values, okay, let's just phrase those down. You've got alpha over 2 is 27.58711. And then you've got 1 minus alpha over 2 is 8.671676. So you got those two. Now, using our formula, we just plug our values in. So n minus 1 degrees of freedom is 17 times the standard deviation squared times the variance over our value. So we've got 27.58711, and that's going to be our lower bound, which comes out to, I believe, 66.651418. Okay, so that's our lowest bound for the variance, and then our highest bound is going to be the same on top, 17 times 10.4 times squared, and then divided by the 8.67176, which gives us roughly 212.0353884. There you go. So that's your lowest here and your highest here. Okay, so that's the interval, yeah. Is there anything else to that question? No, that's good. What assumptions have we made? We are assuming that it's normally distributed, more or less that, like, actually I was sort of wrong saying it wasn't normally distributed. It's technically normally distributed. This is, the chi-squared is just a way of sort of working with it. Yeah. So we're assuming that this precept holds when talking about it. So we're assuming that this is correct, so that it roughly follows a chi-squared distribution when we're talking about the sample divided by the real variance. We're assuming it roughly follows a chi-squared distribution. That's essentially it. That's what I got at the very least. I don't know if that's entirely rigorous, but that's what I did. Right. Then then it's more of an explanatory question. What does it mean to be unbiased versus efficient? So unbiased means it's on average correct. So again, I think I use an example here. So you have the values 0.9, 1, 0.2, 0.4, 0.1, and 0.4. Now, on average, these reach 0.5, okay? But so do 0.55, 0.48, 0.68, 0.52, 0.47, and 0.37. These are both unbiased, meaning they are on average close to what we want to estimate, which here is 0.5, okay? So assume we are estimating a mean, and we want to estimate as close as possible to 0.5. Both are unbiased, but the crucial thing here is that the second one is more efficient, mostly because it is consistently getting closer to 0.5 than the other one, which is sort of bouncing around, okay? It's not really the same. So for it to be unbiased, it's got to be on average correct. for it to be efficient, it's got to give less errors. Basically, it's got to be not that far off. Okay, the more efficient it is, and the more unbiased it is, the closer we're going to get to accurately predicting that value every time. Okay, we're nearly halfway through. Suppose we have a random sample of this number of observations. This one took me a while. Yeah, so, oh god, okay, bear with me here. So we are, first of all, okay, so let's read this. We have a random sample of observations ranging from x1 to xn of the number of seconds. Hold on, am I still in frame? Yes, I am. So we have the number of seconds an advertisement is shown before movie screenings, and we have the sample mean, x over line, to estimate the population mean. So we're estimating the population mean. Now we know the formula for this already, but we kind of have to prove it. Suppose we know that this is normally distributed, okay, with known variance. So we are calculating the mean with known variance, okay? Describe, using math, how to construct a confidence interval. So first of all, let's assume this is normally distributed, which gives us the following. Okay, so we're assuming it's normally distributed with a mean of mean, yeah, and we've got a rough variance of the variance over n. Okay, we're assuming that first of all, and we can normalize this as a matter of fact. Okay, by using our trusty z thing, which is just sample minus mean over variance, which is going to over standard deviation, which means we can normalize it as this. Okay, square root of n. Okay, I think I got that. Yeah. Oh, ignore. I've made a mistake there. Hold on. Square root of n. Latex coding, man. It's just so irritating, right? Okay, so we have a confidence level of confidence levels are normally defined at 100, 1 minus alpha. Okay, and in this case, given it's 95%, the confidence, the alpha is going to be 0.05. Okay, so we got that value squared away. So what we're going to do now is we're going to, we assert, essentially, given that this is normally distributed, that, yeah, so let me just look through my working. Using our confidence level, and given that this follows a standard distribution, okay, we're going to assume that given Z follows a standard distribution, that the chance of it being larger than Z alpha over 2, which, as you remember, is our area below that alpha over 2, which is going to be 2.5. So the chance of it being below 2.5% is going to be alpha over 2, as we mentioned. So then we've got Z is larger. Okay, and given it's a symmetric distribution, it should also be alpha over 2. But what if we combine this? Okay, hold on, wrong way. Yeah. So the chance that Z is below alpha minus 1, and the chance that it's above the high one, okay, means that these two combined are the chances of that interval. Okay, so, all right, what we're going to do here is that, yeah, so we've got the entire probability here, okay, because remember we're thinking about the entire probability in total. So given each of these little areas, then the major area, the interval here, should be, so it's 1, because that's the whole probability, minus these two. So alpha over 2 minus alpha over 2, which gets you 1 minus alpha. Now the intuition behind this is a bit tricky, so let me draw it out, okay? So we've said that due to our current things, we've got P, Z is less than minus Z alpha over 2, and that is alpha over 2. And then you've got the similar thing here. We've got Z is larger than Z alpha over 2, which makes this alpha over 2. So we want to know what this is, right? And given the entire thing is 1. 1 minus these areas gets us 1 minus a for this area. Okay, so we know the entire interval that's accepted is 1 minus a. Okay, so now what are we going to do? Well, we also know this is true, right? So let's bring that down. First of all, let me erase that. And erase the front of this, and then bring it up. Can you do it? Maybe not, but you can try this time of night. It's not good for my health to do this, but I do it. Yeah, there we go. Okay, so moving on like this, we remember that what z was equal to. It was equal to sample mean minus mean over the standard deviation, which was standard deviation over root at n. So we're going to insert that into here. So we've got, oh, come on now. Okay, so we've got the interval here. So we've got minus z alpha over 2 is less than, and we're going to insert that value we got earlier, which was x over line minus mu sigma root n. Okay. Now, it may look like a mess right now, but now we're going to times each side by that denominator there. That gives me negative z alpha over 2, m sigma over root n, less than, you kind of can see where I'm going with this, I think. Don't know if this is entirely a valid solution here, but we're going with it. And then we are adding the mean. Okay, so we're adding the mean to both sides, so we get the mean minus z alpha over 2, and then you got that, root n is less than x dash, then it's less than, oh dear. Does that work? Is that what I wrote? Oh no, sorry, we don't want to include that. Ignore that. We're trying to calculate the mean, so we need to move the x over line. So we're going to minus x over line from both sides, which gets me minus x over line. This it's the other way around, because we know what the sample mean is and we don't know what the mu is. I always like mu. It always sounds like a cat, and I always liked cats. This is useless information. Okay, and we're basically going to flip the signs. Now, if you remember from GCSE, A-level, IB inequalities, whenever you flip the signs in an inequality, all those signs switch. So when we flip the signs, as we're now going to do, we are going to switch the signs around. And we're going to get x minus z alpha over 2. Now, of course, this doesn't look the nicest, okay, but you can kind of see the logic here. Also, if you kind of look at it in reverse, so z minus the margin of error, which is defined as like this thing over here, okay, so z minus that margin of error is going to be smaller than the mean, that which is also smaller than z plus the margin of error. So that's how we sort of prove it. We can sort of rearrange this into a principle, which is where mu lies in the interval where the sample mean plus or minus z alpha over 2, and you got that. No, that's not it. There we go. Okay, so it's roughly like that. Okay? Okay, I hope that helped. Now we want to know, yeah, and we also want to say, oh yeah, because it's also a 95% confidence interval. So if you guys remember from 95% confidence interval from the first question, the value of z alpha over 2 for that is 1.96. So we're going to say it's like this. There we go. That should be right. Yeah. And so you'd get an interval, as I'm sort of saying there in my question, of 1.96. And then you've got this. Yeah, so that's going to be your interval. Huzzah! Now, what are we going to do? Oh yeah, so, right. So for the, oh, this is the old one. Oh, hooray. So now what if the variance is unknown? So this is a bit of a trickier situation, but what we're going to do here is instead of using the known variance, we're going to use our sample variance at S. So we're going to say that we don't know that. So we're going to use sample variance and our sample mean. Now what we do use for this is the t-distribution. Now I would advise you guys to look up students' t-distribution. It's in the slides for week something. It's somewhere. But student t-distribution is sort of like a type of flatter distribution, which we can use, especially in this case. Like, as we previously said, we can normalize it in the same way. So we have x minus mu and s over root n, as we sort of said before. Oh yeah, because it roughly follows that we've got a distribution of means of roughly a t-distribution, which is going to be, in this case, mu and then s squared over n. So this is our mu distribution, and because it's a t-distribution, we're going to use, it's the student's t-distribution, we're going to use t, which gives us that. Okay, then we're pretty much going to get the same thing from before for our given confidence level, which is, once again, p. Okay, remember, actually, with the t-distribution, you've got to have your degrees of freedom. Okay, so in this case, we have So the degrees of freedom, which is represented by n minus 1. So we have n degrees of freedom, so it's going to be n minus 1 degrees of freedom. So we're not only going to put t n minus 1 on everything, but it's going to be t n minus 1 and then our given confidence level. So as you can sort of see here, we're going to get t n minus 1 alpha over 2, which is going to equal alpha over 2. Again, this is the higher one. And then for t n minus 1, divide. Sorry, I'm really tired. Was that minus 1? If it's larger than, what if it is smaller than, yeah. Okay, so this is the minus 1, I swear. What is the probability? Yeah, that's probably it. So combining those, again, we get the same sort of interval, which is where probability of t minus, oh, sorry, I'm really tired. That's no excuse though, is it? And then we've got that. And then, as we said before, that's going to be equal to 1 minus alpha. Okay, so now we've sort of got that. Okay, now we're going to, again, put in our distribution, as we said before, which, as we saw, was, actually, oh yeah, we're still calculating for mean. So it should roughly be the same thing we got last time, so I'm just going to shortcut it. And you should get, to be honest, if I repeated this, I very well could, but it'll take me too long. And it's 2:30 in the morning, and I need sleep. So you should have something that roughly works in this interval. So you've got, it's larger than the minus t-distribution, and then smaller than the sample mean plus the margin of error with the t-distribution. Okay. Also, I'd recommend using an online calculator for the t-distribution, mostly because it's not on most calculators. I found one here. Is that it? There it is. From StatTrek. What a funny joke, right? And you want to use probability. Okay. Yeah, so you've got degrees of freedom. In this case, if we had like 20 people, it would be like 19 degrees of freedom. And if it was a 95% confidence interval, then alpha would be 100 minus 95, which is 5, so 0.05, and then divide that by 2, so 0.025. And so our t-score would be negative, right? So that's what we're going to use. Is it negative? No, wait. No, you use the objective value of it, pardon me. So it would be 2.093, not minus 2.093. Don't use the negative value. Don't do it. It's not very good. I'm so tired. Oh my god. Okay. Now we're unwilling to assume that the distribution is normal. Wow, great. What did I write for this? Oh yeah. What did I say? Oh, also for B, it says how does your confidence interval differ when the variance is unknown? Okay, well, it's getting larger is the main thing. As you can sort of see here, the value of t, especially for limited values of n, is much bigger, which means you're going to have a wider confidence interval than before. Okay, you can see here if we had 10 people, for example, you can see the z value is around 1.96, like we previously calculated, and the t value is around 2.2. So the confidence interval would be significantly higher than a regular, like if we knew the variance. Okay. Of course, this decreases if you gain more and more people. By the time we get like 10,000, 100,000 people, is essentially eliminated. But that's just something to say. When your confidence interval differs, how does your confidence interval differ with when variance is unknown? Yeah, it gets larger, essentially. When we don't know variance, it gets larger. Suppose you're unwilling to assume. Yeah, so to maintain see, the thing is, say we didn't have a normal probability distribution. Say it went like, ooh, like that, or it went like that, or something weird like that, you know? If we wanted to calculate 2.5 on each side, it would have to be at non-symmetric parts, okay? So assume we had like the symmetrical thing here, okay? This wouldn't be symmetrical. The bulk of the graph is lying over here. And then even if I wanted to get 2.5, it might lie here, which wouldn't be symmetrical as it wasn't covering things in a symmetrical manner. So it's not really going to be a symmetrical go. Now this is different from, to construct a symmetric confidence interval now, we'd have to find the area that covers 0.95 or whatever of that distribution. So you would do a cumulative function here, which I would probably call it would probably be consistently getting bigger, and then it would plateau, and then no, that wouldn't be it. So it's, and then less, and then it would sort of plateau out. I think that's how it works. No, actually, that wouldn't be. Don't take my word for it. But let me just read my thing. Given that it's not necessarily symmetrical, giving each end 2.5 would result in unequal distances from the mean. So it wouldn't necessarily work for this as our previous methods. Our previous methods rely on the fact that it's a symmetrical distribution, and in this case it's not. So it wouldn't really work. In A and B, because it was symmetrical, it worked for them. But given that we have a random one, it might not work. So for example, say I had a distribution, like a very dramatic Poisson distribution, like something like, something like this, where you've got, so that's your distribution. It would have to be very close for the 2.5 here, and then once the majority was covered, it would be over here for like the regular 2.5. So again, wouldn't be great because it's not symmetrical, okay? Because the question is specifically telling me, how could you construct a symmetric 95% confidence interval now? It's pretty hard to do so because, like, for it to be symmetric, again, it has to be equal sides of the mean, right? And if that distribution isn't symmetric, then it's not going to be really possible to do otherwise. I don't know for certain. If anyone has a better idea, please do tell me. But this is what I'm going with for now. Okay, question 5. I have these in a different file, so let's go over these. Right. Did hear quite a few people getting problems with this. A random sample of 10 economists produced the following forecasts. What is a point estimator for the following things? So we've got population mean, population variance, and the variance of the sample mean and the population proportion of at least 2.5. Okay, so how would you predict population mean? Well, there's quite a simple way. It's just sample mean. Of course, the larger your sample is, the better, but this is a point estimator, okay? As you can sort of see here, the population mean you should achieve is roughly around 2.57, okay? Again, if we want to calculate population variance, the best calculator is sample variance, shockingly enough. So that's going to be around 0.512 reoccurring. Okay. Now, some people got stuck on the variance of the sample mean, which I was also stuck on. But if we look at the distribution, normal distribution with mu, and then variance over n, then that is our variance. It's variance over n. So how many people are there? There are 10. So that value is going to be 0.0512 reoccurring because we divided it by 10 from our previous one. And then we're going to do the final one, which is D. And then we've got the population proportion of economists predicting growth of at least 2.5. So let's count. So this one is bigger. So 1, 2, 3, 4, 5, 6, 7. So 7 out of 10 economists. Okay, so 7 out of 10 is the sample proportion. Okay, I believe, yeah, that's the best. The best predictor is sample proportion. So we're going to say that pi, which as you guys might remember is real proportion, because, why not? So pi is roughly around 0.7, or 7 out of 10. Okay, those are point estimators for you. Quite all right, I think. Yeah, let's move on. Again, if any of you guys need more detail, feel free to text me. How much do students pay on average for textbooks? So from a random sample of, let's do it as we go along, n equals 400. The mean cost, sample mean, was found to be 357.75, and the sample standard deviation was found to be 37.89. Assuming the population is normally distributed, find the margin of error. The margin of error. The margin of error. Okay. Oh, wait, hold on. Oh, I did this wrong. I did it wrong. Did I? I think I did. Ooh, damn. Yeah, okay. See, what happens here is that some people may get this confused with, which I did as well. Some people get it confused with the regular one here, so just calculating population mean. Whereas because we don't know the variance here, we have to use the t-distribution. So what we're going to get is that our interval is going to be sample plus the t n minus 1 a over 2 sample mean over root of n. And we're going to get the opposite on the other side. Alpha over 2 s over root n. And that's going to be our distribution there. Okay. So, yeah, if I phrase this as one equation, actually, let's figure out that value of t. So t n minus 1 alpha over 2. So this is for a 95% confidence interval, meaning alpha is going to be 0.05, and then alpha over 2 is going to be 0.025. Okay? Obviously, we're going to do the 1 minus version later. Is it 1 minus? It is 1 minus. Is it the 1 minus version? I'm not entirely sure. Okay, well, the degrees of freedom are 400, which was the number of people, minus 1. Let's kill that t-score. And the probability is 0.025. And we get a t-score of 1.966. To be honest, that is pretty close to our 1.96 from before. But again, it is different, so we're going to do it. So we got 1.966. What if I do the other one? I think it's symmetric, but I'm not sure. What is the situation? Let me know, crystal ball. It's not. It's not the same. Ah, okay. So it's... Yep, okay, so it has an error. Damn it. Okay, so we've got to use 1 minus alpha over 2. So that is going to be 1 minus alpha over 2. Actually, hold on, let me pause and double check this with the slides. Just one moment. Nope, I was right before. Let's just show you guys what I meant. Yeah, if you can kind of see here, try zooming in. Yeah, no, that's not it. There it is. You can see it's minus that t-value and then plus that t-value. It's not 1 minus alpha over 2. So we didn't get it right the first time. Cool. Which means we are going to not do the 1 minus. We're going to just do minus and plus. Okay, so we've got plus and minus. Cool. And we've got our value at alpha over 2. Which I think I did. What did I do last time? I'm realizing I got some things wrong. This is horrible. How dare I be a human? This is a complete shock. Yeah, I didn't even use the correct value last time, so just ignore me entirely. But what we're going to do is we're going to get... Yeah, so let's get our values back up. So we've got 3... Oh my lord. Okay, so let's phrase this as one big thing. 357.75. That's correct, yeah. So plus or minus the 1.966 multiplied by 3789 over root 400. Et voila! This is our margin of error. Remember, the question only asked for... Hold on, why do I have such a look going on? So, I guess I'm just hot. Ooh. Assuming that the population is normally distributed, find the margin of error for a 95% confidence interval, population mean. There we go. That is our margin of error. And if we calculate it, we will find that it is the 1.966 times by 37.89 over root of 400, which I believe is 20, but I'm just going to write root of 400 just to be safe. And you should get 3.72 dollars. Remember the context of the question. It's the textbook purchasing. Okay, so that's roughly the confidence interval you'd expect. $3.72. What did I get in my question? 3.71. Oh god, that was a 1 penny off. Oh no. Right, so question 7 now. Oh, my back. I have the back of a 52-year-old, and I don't enjoy it. So what we're going to do is we're going to cover this last one, and then I'm going to go to bed, as you can probably see behind me, because I'm so tired. Suppose that 200 statistics students, okay, starting off, n equals 200, play volleyball with an inflatable globe, and that each student touches the globe only once. Each time a student touches the globe, they yell out land or water, depending on whether their right thumb touches land or water on the globe. The lecturer records the data and reports that 125 students touched water. I feel like that's an offensive thing. Oh, go touch water. I will. Thank you. So we're going to call our sample proportion, which is the proportion of units that touch the water, 125 of 200, just to make it simpler and easier for us to write out later. I'm going to call it as, what is that? 0.625, I swear that is. Oh God, I think I've just realized what this is great because it's basically just debugging my entire mistake process. See here? I wrote it as 0.7, like an idiot, when I should have written 625. Oh God, I've got to correct this after. Oh my God, hold on. Equation 0.625. God, I hate myself. Oh, where is this? 625. Oh, that's so annoying. Oh, God. Oh, wait, that's... Hold on. Calculator. Just checking if I actually did this right. Yes. You know, I'm not even annoyed that I got it wrong. I'm annoyed that I have to do it again. Okay. Well, regardless, we still have our formula, which gives us... Okay, also, we have a 99% confidence interval here, which means that that alpha is going to be 0.01, quite a small alpha, which means we're going to have to divide it by 2. We get 0.005. I think that's what you get. Yeah, that is what you get. And we're going to have to use that for our inverse operation. So what I'm getting here, as I insert that value in to the inverse normal, so I'm inserting 0.005. Yep. As you guys can kind of see there, it's gone down to standard form. A bit weird. I don't know if you guys can actually see that. Hold on, let me just check. Does that work? It's kind of got the, like, I don't think you can barely see it, can you? Oh, that's annoying. But I've put in 0.005 into it, and it's giving me the value of 2.575 stuff. So we've got Z alpha of 2 is equal to 2.575822936. Okay, and with this we can use it. So we're going to get our real proportion, or at least the confidence interval for it, which is going to be modeled by that 2.58. Do we want to just use 258? I'm going to use 276 as a rough approximation. And then we're going to, hold on, let me zoom out a bit more. There we go. And then we're going to put it in the square root with 0.625, which is annoying. 0.625 minus 0.65, and then over the sample, which was 200. And hooray, we have done it. You should get... So annoyed with myself. You guys have no idea how annoyed with myself I am. I'm livid. Livid. Livid, some might call me. So... Yes, hold on one moment. I'm just going to write out the full thing. In the meantime, how was your day? Hopefully you guys aren't getting too stressed. I know it's a difficult time, you know. Lots of people are entering uni for the first time. Everyone's having a difficult time adjusting, you know, social stuff. It's all pretty tricky. I know I found it difficult myself. But hopefully we can all kind of get over it. Hopefully. Yeah, we're seeing a confidence interval of... So that's the high end. So I'm just going to write the high end one in. So we've got 0.7131775016. And we've got, for the lower one, allow me to just swap back on my calculator. Come on, come on. There we go. The lower one is that 0.5368224. So this is our confidence interval for the percentage of Earth that is covered in water. How lovely. So between 53.7% and 71.3% of Earth is covered in water. I think it is actually 71%. So that's pretty good, I guess. So yeah, ignore my workings out of the board right here. But why it's not representative is still valid. So why it's not representative is that, like, imagine, like, I've got a ball here. Okay, the size of the ball depends on the area my thumb presses over. As we can see here, it says we're measuring when their right thumb lands over land or water. When your thumb is quite covered over it, it might not be entirely if you cover your thumb, especially on a small ball, it can cover a lot of area at once. So it might be more inaccurate because you might register land as sea or sea as land or whatever you're doing because the thumb is not accurate. You've also got the problem with the size of the ball. So if I have a massive ball, what is it? What are those balls that people bounce around in on bodies of water? Zoom balls or anyway, whatever they are, massive balls. I'm going to get demonetized for saying this. Anyway, the massive balls are an issue. It'll be accurate if you touch your thumb. If it's a bigger globe, then where you touch it, it's going to be easier to sort of work out. But if it's a massive ball, it's harder to move around, okay? Which means it's going to shift less when you pass it to another person, okay? And if it shifts less, that means lots of people will be pushing at the same area a lot, okay? So they're moving, so with these 200 students, they're all going to have a similar area with the big ball, although it's going to be accurate. And with the smaller ball, it's going to be more varied, but they're all going to be pressing a bigger area with their thumb, which might make it more inaccurate. So yeah, that's my 2 cents about that. Okay, how much time did we take? You know what, that's not actually too bad. I expected worse. Okay, well, hopefully that was helpful, guys. I am so tired. It's nearly 3 a.m. But yeah, I hope that helped. Yeah. Thank God I actually said that because I was so confident and now I realize I was entirely wrong about the last question. Cool. Okay, yeah, I'm going to go to bed. Or maybe I won't. It's a mystery. Anyway, good night. Bye. Not good night. Wait, when are you guys watching this? Good afternoon, good evening, good night. Fuck.